Okay, so here is the video mini lecture to accompany the section 5.3 reading in the textbook. And this is the section that teaches you or explains the idea of elasticity, okay, and you know, spring forces and that type of stuff. So let's give you a quick summary of that. Let's give you a quick summary. All right, so what we're talking about now is we're talking about elasticity. So things that stretch and squish and bend, this type of thing. Okay, so things that squish and bend. And so I think in an earlier video mini lecture, I talked to you about what if you had a spring, and let's say you had a mass on the end of it, or maybe not, but let's say you have a spring and you want to either stretch it out or you want to compress it. So if I stretch it out, the description is very similar. So imagine I stretch this thing out so that now it looks like this. So I stretched it. And the distance that I stretched it, is this distance here. So we're going to call that delta x. And so think about what happens when you pull on a spring. The spring, as you stretch it, the more you stretch it, the more it pulls back the other way, right? It pulls back in response to you pulling on it. And so if we want to know what the force is, again, we're just working in one dimension. So that's going to be the negative of some constant times this delta x. And delta x is defined as the x final minus x initial. So if the final, right, so it's x final minus x initial. So if it started out here at x initial and ended up here at x final, then you take the final minus initial, that gives you the delta x. And so in this case, if our positive direction is to the right, this is going to be a positive quantity. And so when we calculate the force, we have this minus sign to indicate that the force is going to point to the left if we actually did this. Okay, and so this law that describes the force you get by stretching or compressing a spring, this is known as Hooke's law. And of course, it's named after Robert Hooke, the scientist who lived, I believe, in the 17th century, a British scientist from the 17th century. He was a contemporary of Isaac Newton. Actually, they didn't get along, from what I hear. But that's another story. Okay, so that's Hooke's law. Now the thing is, a spring is not the only thing that you can stretch or compress, and get forces that behave this way. Pretty much anything made of matter can be squished or stretched, or even bent or twisted, and it will always respond by producing a force back the other way. This is just sort of the nature of how matter behaves. And so we could imagine a situation in which we have, let's say, some sample of material. I'm just going to draw it as a cylinder, say. Okay. And so we have some sample of material, and let's say we took it and we yanked on it, and we stretched it out. So it started out at this length, and by the time we were done stretching it, it had this length. Okay, we stretched it out to here, right? So imagine we stretch this thing. Right, so this is stretched, okay? So imagine the amount by which we stretch it, we'll call that length of stretch delta L, and we imagine that the original length that it had to start with, we'll call that L0. So, right, this original length is L0, and then this amount of stretch is delta L. And so it turns out that, you know, provided you aren't stretching it too much or too little, right? You're stretching it, you know, a decent amount, but not too much. The relationship between the amount of stretch and the amount of force it took to achieve that stretch is going to look something like this. Let's see here. F over A times L0, like that. Okay, and so what we have here is we've got this quantity here is the amount of stretch. Okay, and this right here, that's the amount of applied force. But just the magnitude. So for this one, I suppose I could put a minus sign to indicate that the direction of the applied force is opposite to the direction of stretch. Or no, sorry, the direction of force with which the stretched material pulls back on you is opposite to the direction in which it's being stretched. Okay, but what I'm doing here is I'm just focusing on the force that you applied, and just focusing on the magnitude of the stretch, right? So I'm not going to carry around a minus sign like I did up here. It just makes things a little cleaner. And so that's the applied force, and then this right here is the cross-sectional area. So what's that? That's this. The area is equal to A. Okay, so this cross section has a certain size of area, and I've shaded it in, and that's this A that appears here. L0 is the original length before you stretched it. Some people call it the relaxed length, original length. And then this Y, this is known as the Young's modulus. This is known as the Young's modulus. And it's named after an English scientist by the name of Thomas Young, who lived in the late 18th century. He did a bunch of different physics on a bunch of different topics, but one of the things he's famous for is you know, stretching things and figuring out and compressing them and figuring this out. And so what is this? Young's modulus is basically a constant. It kind of plays almost a role like the spring constant, which characterizes the stiffness of the spring. So the Young's modulus basically characterizes the stiffness of the material that you're stretching or compressing, you know, by an amount, and seeing how much force it takes to stretch it by a certain amount, or compress it by a certain amount. And different materials are going to have a different Young's modulus. And if you look in the textbook, there's actually a table given of the Young's moduli of different materials that are subjected to this type of stress. So this type of stress, stress to a physicist is actually just amount of force per unit area. Okay, amount of force divided by area. So that's the stress. And this type of stress that you use to lengthen something or squish it down in a lengthwise fashion is known as compressive or tensile stress. Okay, so if you pull it taut and you stretch it, that's called tensile stress, right? You apply a certain amount of force per unit area to this object. That's called tensile stress. And if you squish it down, again, longitudinally like this, that's called compressive stress. And the relationship, of course, between the amount of compressive stress you get and the amount of compression or elongation that you get is given by this relationship. Now, this relationship, as I said earlier, only holds for a certain range of compressions and stresses. And so there's a very nice graph that they show you in the book. There's a very nice graph that they show you in the book that looks something like this, where you have delta L and F. And so, at first you aren't applying very much force, and you barely notice anything happening. But then you see that the force and the elongation become linearly related. And so it starts looking like a straight line. And then after a while, it kind of runs out of steam. It kind of stops increasing linearly. And in fact, it starts going the other way. And then at some point it breaks, right? So you reach, this is called ultimate stress, when you apply so much force that you break off a piece, okay? And so this region here, this region sort of between this point here and this point here, this is the linear region in which this formula applies. So this is the linear region. Okay, and so then that's sort of your compressive and tensile stress. Now there's two other types of elasticity that they talk about in the book. So let me just quickly go over those. So the second one that they deal with is known as shear. So when you shear something, you're basically applying a force to it, but in an uneven way. Okay, and so so what happens is that you have something, let's say, that starts out kind of being, rectangular, and then what you do is you pull on it in one direction at the top, and you push on it in the opposite direction at the bottom. And so what winds up happening is that you sort of stretch it, you deform it in this particular way. So you deform it kind of like this. Okay, so I apply a force at the base like so, and I pull on it with the same force. Okay, like that, and so I end up deforming it in this way. This is called a shear deformation, and we can describe the physics of this by saying that there's this amount of deformation horizontally, right? So this point ended up over there, right? So it moved by that amount, and we can say that the height of this thing, we'll call that L0, right? So now the L0 has a different meaning from what it did when we were talking about tensile and compressive stress. And then we can imagine, just imagine with me for a moment, that this, you know, the top of this object, you know, has this shape, okay? Right, so imagine the object, you know, so I'm trying to draw it sort of in 3D for you here. Right, so it was like this and then it got shoved over, you know, deformed in this way. And so if we imagine, you know, the top of it has a certain area, right? So here I'll draw the bottom face, right? And then we'll sort of shade it in, right? So the bottom face has the same area as the top face. And we say that the area of the face is equal to A. So we can put all these together and we find that the description of shear stress is 1 over S times, or sorry, the description of shear deformation is 1 over S times the amount of force, right? So now this F is this F, and times L0 like that. And now this right here is what we call the shear modulus. And so this is going to be different for different materials, right? I mean, if it's a piece of bubble gum, you know, it'll have one value. If it's a piece of wood, it'll be different, right? You know, bubble gum is less stiff than wood. You see, and so it doesn't take as much force, you know, doesn't take as much stress to shear a piece of bubble gum as, let's say, it does to shear a piece of wood. And so that's what all this means. And so then last of all, what they have for you is they've got bulk stress. And so for bulk stress, what we're talking about is, imagine you have a cube, okay? So there's our cube. And then what we do is we go ahead and we apply the same force evenly all around. The same exact force. We just squish the heck out of this thing. Okay, we apply the same force everywhere. We're just going to squish the heck out of it. Okay, even, you know, from the front and back. We apply force from the front and back as well. So we squish it, and we do it so much that what happens is that the cube gets smaller. It becomes like this. Okay, we squish the heck out of it until it becomes smaller. Okay, squish it from all sides until it becomes smaller. And so what happens is now the volume went from being this large volume to being a smaller volume. And so what we would write is that the change in volume is given by this equation. And so now what we have is that this is the starting volume, and then this here is known as the bulk modulus. And this here, of course, is the change in volume. Okay, and once again, just as with tensile stress, you know, this equation and this equation, they only really apply within a region where you aren't stressing it too much and you aren't producing too much of a big deformation, a big change in the volume and or this change in this displacement of the edge of the shape that you're deforming. Okay, and so because at some point, at first, if you don't apply enough force, you don't notice any effect, right? If you apply too much force, you basically rip off a piece. Okay, so somewhere in between, there's a region where it's got this very nice linear relationship between the amount of deformation and the amount of applied force.